Episode 9. Title of the Radio Enable Learning course is Energy Physics. Unit 3. In this unit, we will discuss about wind energy, basic principles of wind energy conversion, power in the wind, forces in the blades, wind energy conversion, advantages and disadvantages of wind energy conversion system, WECS, energy storage and applications of wind energy. First of all, I will introduce about wind energy. Wind results from air in motion. Air in motion arises from a pressure gradient. On a global basis, one primary forcing function causing surface winds from the poles towards the equator is convectivity circulation. Solar radiation heats the air near the equator, and this low density heated air is buoyed up. At the surface, it is displaced by cooler, more dense, higher pressure air flowing from the poles. In the upper atmosphere near the equator, the air thus turned to flow back toward the poles and away from the equator. The net result is global convectivity circulation with surface winds from north to south in the northern hemisphere. It is clear from the above oversimplified model that the wind is basically caused by the solar energy irradiating the earth. This is why wind utilization is considered a part of solar technology. In reality, the wind is much more complex. The above model ignores the earth rotation, which causes a Coriolis force resulting in an easterly wind velocity component in the northern hemisphere. There is the further complication of boundary layer frictional effect between the moving air and the earth's rough surface. Mountain, trees, buildings and similar obstructions impair streamline air flow. Turbulence results the wind velocity in a horizontal direction markedly increase with altitude near the surface. Then there is the obvious fact of land and water with their unequal solar absorptivity and thermal time constants. During daylight, the land heats up rapidly compared to nearby sea or water bodies, and there tends to be surface wind flow from the water to the land. At night, the wind reverses because the land surface cools faster than the water. Local winds are caused by two mechanisms. The first, differential heating of land and water. Solar insolation during the day is readily converted to sensible energy of the land surface but is partly absorbed in layer below the water surface and partly consumed in evaporating some of the water. The land mass becomes hotter than the water, which causes the air above the land to heat up and become warmer than the air above water. The warmer, lighter air above the land rises, and the cooler, heavier air above the water moves in to replace it. This is the mechanism of shore breezes. At night, the direction of the breezes is reversed because the land mass cools to the sky more rapidly than the water, assuming a clear sky. The second mechanism of local winds is caused by hills and mountain sides. The air above the slopes heats up during the day and cools down at night more rapidly than the air above the lowlands. This causes heated air that day to rise along the slopes and relatively cool heavy air to flow down at night. It has been estimated that 2% of all solar radiation falling on the face of the earth is converted to kinetic in the atmosphere, and that 30% of this kinetic energy occurs in the lowest 1000 meter of elevation. It is thus said that the total kinetic energy of the wind in this lowest kilometer, if harnessed, can satisfy several times the energy demand of a country. It is also claimed that the wind power is pollution free and that it is source of energy is free. Such are seemingly compelling arguments for wind power, not unlike those of solar power. Although the solar energy is cycle and predictable and even dependable in some parts of globe, wind energy, however, is erratic, unsteady and often not reliable. Except in very few areas, it does not, however, have a place in the total energy picture, particularly for those areas with more or less steady winds, especially those that are far removed from central power grids and for small remote domestic and farm needs. Conversion of the kinetic energy, that means energy of motion of the wind, into mechanical energy that can be utilized to perform useful work or to generate electricity. Most mechanisms for converting wind energy into mechanical energy consist basically of the number of sails, vanes and blades radiating from hub and central axis. The axis may be horizontal as in the more familiar windmills, or vertical as it is in some cases. When the wind blows against the van and sails, they rotate about the axis. The rotating motion can be made to perform useful work. Wind energy conversion devices are commonly known as wind turbines because they have convert the energy of the wind stream into energy rotation. The component which rotates is called the rotator. The terms turbines and rotator are, however, often regarded as being synonyms. Because wind turbines produce rotational motion, wind energy is readily converted into electrical energy by connecting the turbines to the electric generator. The combination of wind turbines and generator is sometimes referred to as an aerogenerator. A step-up transmission is usually required to match the relatively slow speed of the wind rotator to higher speed of an electric generator. Although windmills have been used for more than a dozen centuries for grinding the pumping water, interest in large-scale electric power generation has developed over the past 50 years. The largest wind generator built in recent times was the 800 kilowatt unit operated in France 1958 to 1960. The flexible three-blade propeller was about 35 meters in diameter and produced the rated power in 60 km per hour wind with a rotating speed of 47 rpm. The maximum power developed was 12 megawatt. Wind energy is one of the America's greatest natural resources. The US government could plan for installation of wind turbines generator with a total capacity of 1 gigawatt by 1985. Windmills have been used for several centuries in countries like Netherlands and Denmark, where high velocity wind is available. Nearly 30,000 house mills capable of producing 100 megawatt and 3,000 industrial windmills generating another 100 megawatt were operating in Denmark at the turn of this century. In India, the interest in the windmills was shown in the last 50th and early 60s. Apart from importing a few from outside, new designs were also developed, but it was not sustained. It is only in the last few years the development work is going on in many institutions. An important reason for this lack of interest in the wind energy must be that wind in India are relatively low and varying appreciably with the seasons. Data quoted by some scientists that for India wind speed value lies between 5 km per hour to 15 to 20 km per hour. This low and seasonal wind imply a high cost of exploitation of wind energy. Calculations based on the performance of a typical windmill have indicated that a unit of energy derived from a windmill will be at least several times more expensive than energy derivable from electric distribution lines at the standard rate, provided such electrical energy is at all available at the windmill site. The above argument is not fully applicable in rural areas of several seasons. First, electrical power is not and will not be available in many such areas due to high cost of generation and distribution to small dispersed users. Secondly, there is possibility of reducing the cost of windmills by suitable design. Lastly, on small scales, the total first cost of serving a felt need and low maintenance costs are more important than the unit cost of energy. The last point is illustrated easily. Dry cells provide energy at the astronomical cost of about rupees 300 per kilowatt, and yet they are in common use in both rural and urban areas. This raises the question of that the felt needs are that a windmill might satisfy while large-scale energy production at some favorable sites in India is a possibility that needs to be explored. There appears to be a definite need to small sources of mechanical energy in rural areas. For example, even casual polls among villages quickly reveal that there is first concern is invariable of water for drinking, washing and irrigation, and lifting water is a task which a windmill can perform. For such a task, a windmill should produce about 100 watt. Many projects on windmill system for water pumping and for producing a small amount of electric power have been taken up. Various organizers such as National Aeronautical Laboratory Bangalore, Central Salt and Marine Chemical Research Institution, Bhavanagar, Central Arid Zone Research Institution, that means CAZRI, Jodhpur, etc. Wind energy offers another source of pumping as well as electric power generation. India has potential of over 20,000 megawatt for power generation and ranks as one of the promising country for tapping this source. The cost of power generation from wind farms has now become lower than diesel power and comparable to thermal power in several areas of countries, especially near the coasts. Wind power projects of aggregated capacity of 8 megawatt including 7 wind farms project of capacity 6.85 megawatt have been established in different parts of the country, of which 3 megawatt capacity has been completed in 1989 by DNES. Wind farms are operating successfully and having already fed over 150 lakh units of electricity to respective state grids. Over 25 megawatt of additional power capacity from wind is under implementation. Under demonstration program, 271 wind pumps have been installed up to February 1989. 60 small wind batteries chargers of capacity 300 watts to 4 kW are under installation. Likewise, to stand-alone wind electric generation of 10 to 25 kW under installation. Next, we will discuss about the nature of wind. The circulation of air in the atmosphere is caused by non-uniform heating of Earth's surface by the sun. The air immediately above a warm area expands. It is forced upwards by cool, denser air which flows in from surrounding areas, causing a wind. The nature of terrain, the degree of cloud over and the angle of the sun in a sky are all factors which influence this process. In general, during the day, the air above the land mass turns to heat up more rapidly than the air over water. In coastal regions, this manifests itself in a strong onshore wind. At night, process in reverse because the air is cooled down more rapidly over the land and the breeze therefore below offshore. The main planetary winds are caused in much the same way. Cool surface air sweeps down from the poles, forcing the warm air over the tropics to rise. But the direction of these massive air movements is affected by rotation of the earth, and net effect is large countries' clockwise circulation of air around low pressure areas in the northern hemisphere and clockwise circulation in the southern hemisphere. The strength and direction of these planetary winds change with the seasons as the solar input varies. Average wind speed are greater in hilly and coastal areas than they are well inland. The winds also tend to blow more consistently and with greater strength over the surface of the water where there is less surface drag. Wind speeds increase with height. They have traditionally been measured at standard height of 10 meters where they are found to 20 to 25 greater than close to the surface. At a height of 60 meters, they have been 30 to 60 higher because of the reduction in the drag effect of the Earth's surface. Next, we will discuss about the power in the wind. Wind possesses energy by virtue of its motion. Any device capable of slowing down the mass of moving air, like a sail or propeller, can extract part of the energy and convert it into useful work. Three factors determine the output from a wind energy converter. The first one is the wind speed. Second one is the cross section of wind swept by rotator. Third one is the overall conversion efficiency of the rotator, transmission system and generator or pump. No device, however well designed, can extract all of the wind's energy because of the wind would have to be hauled, and this would prevent the passage of more air through the rotator. The most that it is possible is the rotator to declarate the whole horizontal column of intercepted air to about one-third of its free velocity. A 100% efficient aerogenerator would therefore only be able to convert a maximum of around 60% of the available energy in wind into mechanical energy. Well-designed blades will typically extract 70% of theoretical maximum, but losses incurred in the great box transmission system and generator or pump could decrease overall wind turbine efficiency to 35% or loss. The power in the wind can be computed by using the concept of kinetic. The windmill works on the principle of converting kinetic energy of the wind to mechanical energy. We know that power is equal to energy per unit time. The energy available is kinetic energy of the wind. The kinetic energy of any particle is equal to 1 of its mass times the square of its velocity, or half mv square. The amount of air passing in unit time through an area capital A with velocity capital V is A dot V, and its mass small m is equal to its volume multiplied by its density rho of air. Then small m is equal to rho capital A capital V. M is the mass of the air transferring the area capital A swept by the rotating blades of a windmill type generator. Substituting this value of the mass in the expression for the kinetic energy, we obtain kinetic energy of rho A V V square watts. The equation becomes half rho A V cube watts. The fraction of free flow wind power that can be extracted by a rotator is called the power coefficient. Power coefficient equal to power of wind rotator divided by power available in the wind. Then we can define power coefficient, the ratio between power of wind rotator and power available in the wind. There are clear advantages in selecting sites with annual mean wind speeds and building larger rather than smaller wind generator, since the power available in the wind increases as cube of the wind speed. Doubling the wind speed increases the power available by 8-fold. Doubling the diameter of turbine rotator quadruples the swept area and hence the power output from the device. That means this law only applies to horizontal axis machines. For vertical axis machines, the change in power output with diameter will be determined geometry of the rotator. The way rotator diameter and wind speed affect power output. In practice, a wind turbine output will vary. There will be period when there is insufficient wind for the machine to generate any power at all, and times when the wind speeds are so high that the machine has to be shut down to prevent damage. As stated above, that the total power cannot be converted to mechanical power, consider a horizontal axis propeller type windmill henceforth to be called a wind turbine, which is most common type of used today. Assume that the wheel of such a turbine has thickness AB. Let pi and Vi are the wind pressures velocities at the upstairs or upstream of the turbine, and Pe and Ve are pressure and velocity downstream of the turbine. V is less than Vi because kinetic energy is extracted by the turbine. Considering the incoming air between I and small a as a thermodynamic system, and assuming that the Air density remains constant. Dear student, we will discuss about the next topic in episode 10. Thank you.